Okay, so let's do the 2004 mechanics free response question number 1 in mechanics. And here is the test. And it says, well, these are just the directions for taking the test. So it's 15 minutes. But anyway, here's the problem. We got a rope, and this rope has a length of L, and it's attached to a support at point C. A person of mass M1 sits on a ledge at position A, holding the other end of the rope so that it is horizontal and taut, as shown above. The person then drops off the ledge and swings down on the rope towards position B. On a lower ledge, where an object of mass M2 is at rest. At position B, the person grabs hold of the object and simultaneously lets go of the rope, because this could happen. The person and object then land together in the lake at point D, which is a vertical distance L. L, okay, so this is the same as this L. Below position B. Air resistance and the mass of the rope are negligible. Derive the expressions for each of the following in terms of M1, M2, L, and G. I actually like these kind of problems. I don't like using my calculator unless I have to. So, and so A is the speed of the person before the collision of the object. So in part A, oh wait, we're good. So in part A, what are we trying to find? The velocity before the collision. I'll just call that V. And here. And so I think you can see with this problem that it's a conservation of mechanical energy problem, this part, that the gravitational potential energy is going to get turned into kinetic energy here. And so whenever, by the way, they ask for the velocity of something, think about energy right away. It's probably easier than kinematics. You can't use kinematics here anyway, but because acceleration is not constant. But, all right, so E initial equals E final. And then what kind of, we'll say that U is equal to 0 right here. So this is going to be M, and this person is mass M1, is that right? So M1, G, and then H is actually L. I think all of this stuff is in terms of L. It's going to be equal to 1/2 M1 V 1 squared. So the mass cancels out, and so we get V is equal to the square root of 2GL. And that shouldn't be all that surprising. And this is only worth 2 points, if you got that. And part B. And, okay. I can't see it either. Part B. Here we go. The tension in the rope just before the collision with the object. So here our object is moving down like this with M1, and then they've got this speed that we just calculated, that V1. And what kind of motion is this? Well, they're swinging on a rope here, so it's going to be a centripetal motion. If I drew a free body diagram of this guy, you've got M1 times G, and then you've got the tension in the rope. And that's what we're trying to find. If I sum the forces in the y direction, that'll equal MA in the y direction. Tension force minus M1G is equal to M1 But what kind of acceleration is this? Centripetal acceleration. So that's going to be v1 squared over r. But what is r here? R is L. So T is going to be equal to m1. Now let's substitute for v1 squared. That's just 2gl over L. Okay, so this will cancel. Plus m1g. So the tension is going to be equal to, let's factor out the m1 and the g times 2 plus 1. So it's going to be 3. Is that right? Three m1g, and yeah, that's right. Turns out to be right. And if you look at the, I'm not going to go through the solution manual in depth, but here's the solution manual for it. And so that's worth 4 points. So we've got 6 points so far. I think pretty reasonable problem. I think you can do this. All right, now let's do part C. The speed of the person and the object just after the collision. Well, this is an inelastic collision, right? The M1 and M2 are coming together. But we know in a collision that the initial momentum is equal to the final momentum. Very straightforward problem so far. So this is going to be M1 V1, at least V1 initial we'll call it now. And that's this guy over here. And then they're going to move together. So you're going to have an M1 plus M2 times their final velocity. So V final, and that's what we're looking for, the speed of the person, the object just after collision, is equal to M1 plus M2. Oh, I'm sorry. No, that's wrong. We're going to divide that to the other side. So it's going to be M1 times V1 initial, but that's the square root of 2GL over M1 plus M2. And that should be the answer. And that is the answer. Yeah. Okay. And this part was worth 3 points. Now, 6 and 3 is 9. Hey, if you've done this, okay, you're now, at least for this problem, you're into 3 to 4 territory. Okay, so we're doing well. We're doing well. So let's do part D. Right here, and part D says, the ratio of the kinetic energy of the person-object system before the collision to the kinetic energy after the collision. So the kinetic energy before over the kinetic energy after, the initial and final. Well, before, you just had 1/2 M1, and the only thing moving was the person on the rope. So that's that V1 squared, which is going to be, again, this over here, divided by the final, which is 1/2 M1 plus M2, times this whole mess squared. Now I imagine a whole bunch of things are going to cancel out, but let's go ahead and substitute in right now. Well, I'll just call it V final squared, and then we'll substitute in for this and for this. Well, I can cancel out the 1/2s right away. Let's not worry about those. And so now we have M1. Now V1 is the square root of 2GL. Square that, you get 2GL over M1 plus M2 times this big ugly mess squared. And so lots and lots of stuff cancels out. 2GL cancels the 2GL. M1 cancels with the M1 squared. And M1 plus M2 cancels with the M1. Wait a minute. Oh, this should be squared. Thank you. I was looking at that and going, And the way I caught my mistake there, and I did make a mistake, is I was noticing that it's not dimensionally canceling out. You can't have a mass left over. You can't have anything with units left over. But anyway, so this will cancel with this. And so we're left with M1 plus M2 over M1. So that's the fraction, and I think that's as far as we can go, right? Let's take a look. Yeah, that's as far as we can go. So there's the ratio. That's only worth 2 points. That's kind of disappointing. All right, so let's do part E. Try to fit part E in here. And part E says, we want the total horizontal displacement x of the person from position A until the person and the object land in the water at point D. So what they really want is this. Well, obviously we're just going to figure out what this is. I'll call this delta x, and then we're just going to add L to it, and that'll be our distance from here over to here. So, and this is just projectile motion. So we have our velocity here, and it's going to go like that. So let's find this delta x. Well, we know what this velocity is, right? This is, well, I'll just, rather than write out all that stuff, we'll just call it v final from after the collision. Now, we know that delta x is going to be equal to the horizontal velocity times time. So we need an expression for time. So, well, I know that delta y is equal to v naught yt plus 1/2 a t squared. Well, the initial velocity in the y direction is 0. So this goes away. So t is equal to the 2 delta y over a. We're going to call that g now, because they want the acceleration called g. Well, this is good. And what do we know about delta y? Delta y is, it's L. So 2L over here. You with me? You guys aren't saying much. I feel kind of lonely up here. All right. So now delta x is going to be equal to the v final times time. So I can substitute now by big, messy expressions. There's my velocity, and here's the time. And I don't really see anything that cancels out here, unfortunately. But then what are we going to do? X is equal to L plus delta x. So x is actually going to be L plus m1 root 2GL over m1 plus m2 times 2L over g And that's how I'm going to leave it. Now, I guess they, did I make a mistake somewhere? Oh, I did make a mistake. I forgot the square root right here. Okay. Well, I guess this does change things a little bit. Yeah. Because now stuff will cancel out. Yeah, I left this radical off accidentally when I did the substitution. So if you see me doing that, it's okay to cry out, Mr. Lloyd. All right, so this root g will cancel with this root g. This will become L squared, so we have L plus, and the square root of L squared is just L. And then this is just going to be 2. 2 times 2 is 4, this root 4 is 2. And then I think everything else is just M1 over M1 plus M2. And then, is that what they got here? I think this is right. They algebraically manipulated a little bit more into this more simplified form. But you only have 45 minutes to do these problems. You have 3 problems to do in 45 minutes. So this accomplishes the task. It expresses what they want in terms of the masses and the length of the rope. And that's all they asked me to do. So I'll stop there. So let's review what the big ideas here are. Okay, for part A, the big idea is conservation of mechanical energy. Okay, so you need to be able to recognize when to use that. What's the big idea here? Well, free body diagrams and centripetal force. And centripetal force for a vertical circle. And you'll see those a lot. So you might want to review centripetal force for vertical circles. And then in part C, after they hit, obviously, conservation of momentum during collision. Collisions and conservation of momentum. Part D, just kinetic energy and taking ratios. Of course, you have to depend on previous answers to make that happen. And then part E is projectile motion. So this is what they like to do on AP test. You've covered a big chunk of all the ideas that we've talked about. There's energy, centripetal force, collisions, momentum, projectile motion. That's a lot of stuff in one 15-minute problem. But I think once you look at it, you go, okay, that problem's not so bad. That is all.